So today's class is only like a small doubt clearing session. So it's not like all assignments are over anyway. So you might have submitted a lot.
Pardon, Rahulji?
Uh, Today is only like a doubt clearing session class. Okay, so
Okay,
we will
okay,
be
okay,
so we will be revisiting some of the old concepts.
okay, okay, fine, fine, fine.
Yeah, that will be like that. Okay. Okay, then welcome everyone. This is the doubt clearing session class for polymer reaction engineering. First question. From the beginning, we'll be seeing three questions and we'll be going through them one by one. And we are going to see what are the different problems we came across through this entire lecture series. So the first one is for polydispersity index, which statement is or it is the ratio of weight average molecular weight to the number average molecular weight. Second one, it is usually one for the monodisperse polymer or greater than one for actual polymer. And the third one is it is used as a measure of broadness of molecular weight distribution.
It is MW by MN, like weight average by number average.
Yes, yes, exactly. MW1. So, as you said exactly, it is option. Option one is the correct one. Weight average by number. But in the second one also you can see that it is usually one for non-disperse polymer and greater than one for actual polymer. That definition is also true
Okay, correct.
because
That is correct. Mono disperse means it will be one. Yeah,
yeah,
narrow distribution.
exactly. Mono-disperse means normal. And it will be a narrow disperse.
So it is like a MSQ multiple choice options.
Yes, yes, yes. And in the exam also you will be getting multiple choice options. Questions.
Okay, okay,
Yeah. So yeah. And most of the problems in this lecture series are more or less like if you go through the notes, you'll be able to make sense of it. Is they are quite easy.
okay, okay, okay.
Okay. Then next we have completely amorphous polymers showed only the glass transition temperature. Crystalline polymer showed melting temperature, and semi-crystalline polymer exhibit both temperature. So here we have two diagrams, and we have already gone through this concept also that completely amorphous polymers, what happens with them is that they show a glass transition temperature. They go from their glassy state to a rubbery state. So when the molecules start to move, since they are already amorphous in nature, so the molecules are free to move. Once they start moving freely, they undergo the glass transition phase, and then return to the rubbery state. Whereas crystalline polymer shows the melting temperature. What happens with crystalline polymers is since their arrangement is in orderly manner, uh, the melting of the polymer occurs quickly, and because of that, they don't show the glass transition. They only show the melting temperature. And since all polymers are semi-crystalline polymers, they exhibit both glass transition and melting temperature. So this statement is true.
Yeah, this is clear. Yeah, we are having like amorphous means it is only TG,
Yeah.
whereas crystalline it is TM, and
Yes.
semi crystalline it will show both.
Both. Yes.
Yeah.
Exactly. Exactly. And next one we have if the recycle ratio R is zero, then the recycle reactor approaches to plug flow reactor, and the performance equation of the recycling reactor will become the same as performance equation for PFR. So what happens with the recycle ratio is that first of all, what is recycle ratio? Recycle ratio is the ratio of the feed which is going back in the recycle and the feed which is coming out. So if this entire ratio is going to become 1, it means that all of the feed is going back to the reactor itself. It means that what's happening is that the performance equation it will become as a PFR, plug flow rate, because the entire fraction is going to move like a single plug, and that is the exact reason why the performance equation will become same as the equation of the PFM.
This
So
is true.
yeah, that's true. Next question. The average molecular weight obtained in the step growth polymerization is limited by. So in step growth polymerization process, what happens is that the monomer monomers attach with each other and they grow in a sequential manner. So the growth will only go till the point where the growth of the polymer is not favored by the system itself. So if the system has some potential, chemical potential left, only then it will go past the equilibrium point. Or else, if it reaches the reaction equilibrium, the growth of the polymer will stop. So that's why the average molecular weight obtained in step growth polymerization will be limited by its reaction equilibrium. So option B is the correct answer for this question.
Step growth we are primarily like attributing to the equilibrium. As the equilibrium attains, then we are
Uh,
assuming that it is average molecular weight is reached. Or
hmm. Yes, yes. Because all of the step growth polymers will be growing till that extent, and then the reaction will stop because it has attained equilibrium, and it won't cross the equilibrium without any other driving force. That's why.
okay, okay, clear.
Hmm. Yeah. Then we have the fill in the blanks. Electron dash functional groups like dash increase the electron density over carbon-carbon double bond of the system. This leads to facilitation of cationic polymerization of the monomer. So first of all, it is saying that electron functional groups like increase the electron density. So if there is an increase in electron density, which means that this functional group is going to donate the electrons. So the answer will be one of the donating groups. And we can see that there are two options right there. And it is saying that it will increase the electron density over carbon-carbon double bond of the system. This leads to facilitation of cationic polymerization of the molecule. And this can only be achieved by using the alkoxy radical. That is the O group will be there. Nitrile radical is with the CN, NC radical is the nitrile radical, and with the alkoxy radical, which is the electron donating functional group, it will increase the double bond and increase the electron density over the double bond, and it will lead to facilitation of cationic polymerization of the monomer. So option B is the correct answer for this.
Be donating and alkoxy.
Yeah, donating and alkoxy. In case of high viscosity polymers, the size exclusion chromatography cannot be used due to clogging of the reactor by the viscous polymeric fluids. So we have already seen that the characterization technique used for measuring the molecular weight of a highly viscous polymer is equal to is measured by GPC or the size exclusion chromatography. GPC is the gel permeation
Based on the
chromatography.
size only. Yeah, it is based on
Yeah,
the size, the molecular weight, and the GPC is the one best way where we can go up to 1 lakh or more.
yes, exactly, exactly. You can go to that extent. So that's why the answer for this question is false. That size exclusion chromatography cannot be used. It can be. So option for this is false. At very high concentration of initiators, the order the order of the rate of radical polymerization RP dependency on initiator concentration can be found to be less than half. The reason can be attributed to. So there are four reasons listed here, three reasons listed here. First is the resonance stabilization, impurities present in the monomer, and cage factor. So resonance effect occurs only when the functional group which is present inside it is causing some sort of charge distribution, and because of that the resonance stabilization will occur. But that has no role in increasing the order of rate of radical polymerization reaction. And impurities present in the monomer are not going to help it either. But cage factor can be a thing. What is cage factor? Cage factor in this, what happens is that radicals formed from decomposition of an initiator molecule are surrounded by a cage consisting solvent or monomer molecule. So what happens is when the initiator decomposes and when a radical is formed, that radical will be surrounded by the solvent molecules or the monomer molecules. And when this when it is surrounded by this cage of molecules, within this cage, recombination of the radicals can take place and it will deactivate the reaction. So it will start deactivating the reaction. And since the initiator concentration is very high in the question as it is written, that is an effective factor. So pH factor is the factor which affects the rate of radical polymerization. RP. Moving on to the next question.
Yeah, that
What
is
is
clear.
yeah, what is the characteristic that affects the shear and peel resistance to the hydrolysis of the emulsion polymer component? So shear and peel resistance of a hydrolysis of emulsion polymer or copolymer. How is this related? So when a copolymer, any polymer is formed, and if it is undergoing hydrolysis, there is a chance that it will undergo some sort of change. And because of this change agent, it can lose its properties to uh, it like it will lose its property and it will be more susceptible to shear or peel. And because of this, it gets easily affected by the peel action or the shear action. And one of the best ways to make a stable polymer is have a sufficiently high molecular weight distribution. So if there is a high molecular weight distribution, what is going to happen is the molecular weight distribution, because since it is very high, it will have longer chains and larger entanglements, and because of that, the shear and peel resistance will increase. So that's why molecular weight distribution affects the shear and peel resistance of hydrolysis of the emulsion polymer. Option B is the answer for this.
Okay, okay. Here actually like gel content and rheology also was highlighted, but that is
Hmm.
related to one is shear and peel. So here we
Yeah,
are talking about shear and peel only.
yeah, shear and peel. It's kind of like similar kind of action, except that peel is peel means you're directly breaking the any kind of adhesive bond, and shear means it is causing some kind of friction. That is because of that the definition is framed like that. Next
Yeah,
question.
but why we are not attributing to gel content or rheology? Because that I remember there was in class there was an explanation for this.
Actually, the thing is, rheology also is governed by molecular weight only. If you have very high molecular weight, you will have higher rheology or viscosity. So they are interrelated, and everything is happening because of the molecular weight distribution.
Okay, okay, clear.
Hmm. In radical polymerization, sometimes the premature termination of the propagating polymer occurs due to transfer of hydrogen atoms to the propagating polymer from the same solvent or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to what? So because of this, what's happening is let's imagine the scenario that because of the premature termination, before reaching the full length, the propagating polymer will transfer its activity to the uh, other other radical or other node. And because of this, the reaction is getting transferred to the different chain. And again, in that chain, polymerization will start. Again, if in that chain, again, if the activity transfer to some other chain, this will lead potential polymers which could have had higher molecular weight. And because of this, the decrease in molecular weight of the polymer can occur. So that's why option D is the correct answer.
Whether it is decrease in molecular weight or increase in molecular weight, because
Decrease,
it
decrease. It will decrease
because
because
uh,
the
uh,
chain. The chain transfer mechanism will just transfer the activity from one chain to the other, and the moment it will find the counter ions, it will subside.
Rohit, I'm not clear because actually when we are allowing this propagation to happen,
Hmm.
we are telling that it will be terminated through solvent or monomer or initiator. So which
Yes.
means again new radical is formed is due to chain transfer reinitiates the polymerization. So already there is a molecular weight buildup available, and
Hmm.
further it is propagating means it will increase the molecular weight. Na?
Yes. But the thing is, the reason why this happens is because transfer of hydrogen or other atom to the propagating polymer from the same radicals or same initiator will occur. And because of this, it won't be able to reach its theoretical determined value or the maximum molecular weight it could have achieved. Because the chain transfer is simply passing on the activity to the other chains. That's all.
Okay, so here we are looking, and the answer is like decrease in molecular weight.
Yeah, decrease. Decrease or more like we will have a lower actual molecular weight than the theoretically estimated.
Okay, okay. So otherwise, if train transfer is not there, we would have ended up in high molecular weight. Since train
Hmm.
transfer is happening, that is not there. So that is what we are
Yeah, yeah,
trying to. Okay, got it.
exactly, exactly, exactly. Yes. So, yeah, today only these questions were there. They were like a recap to the previous classes, what we saw in the previous classes. So, if you have any doubts or any leftover from the previous classes, you can ask.
Yeah, just want to know because now that we have like probably I don't know about others.
Hmm.
We had like total four courses for this year, and
Yeah.
this one is like clubbed along with on mathematics exam. Like
Hmm.
that is also there in the morning session and the afternoon session. Our class is also there. Just want to know like what is the level of toughness it will be there for an exam because I don't know whether a full time will be there for going through the entire 12-week lecture for revision per se. But though we had a better understanding whether it
Hmm.
will be like it will be answerable by just by recall whether we can answer or it will be like totally new.
No, no. By recalling, you can answer. It's
Okay.
better. It's like that. Like you just have to remember how the polymerization mechanisms work, first of all, how the radical polymerization works, ionic polymerization. So just know the basics of all those things, conserves know, and only general descriptions will be asked for the processes. How, like some special phenomena such as chain transfer effect, cage efficiency, cage factor, and all these things will also be asked, but you will be able to answer them fairly easily.
Okay, thank you so much. And just can you, if you don't mind, if you can just show that yesterday's slide, I don't know whether it is correct if I am asking this way,
Hmm.
because since the lecture is there, if you can just 5 minutes help me to show that so that if any doubt is there, I can clarify.
Yeah, yeah, so yesterday it was about the cationic and anionic polymerization. So like pretty much the final class, and these were the questions which were asked.
Can we just put it in slideshow mode? I will just quickly glance through if any doubt is there, I can.
Yeah, yeah, yeah. Okay, okay.
Steady state assumption is here.
One second. I'll just.
Okay, okay.
Yeah, can you see now? You can see, right?
Yeah.
Hmm.
Steady state assumption is here. Mechanic calibration is here. Okay, so here we are having both options like A and C.
Yeah, yeah, yeah. Yes.
Okay, okay. Next, please. Organic compost substance and chemical formation by formation of the molecule and acid. So now I will need to click the risk to terminate the computation. Ramji, can you please explain this one?
Yeah, what is happening here is that we have a protonic or Bronsted acid initiated cationic polymerization by protonation of the olefin. The anion of that acid should not be highly nucleophilic, otherwise it will terminate the protonated olefin by by combination. So what happens here is that uh, you have a protonic or Bronsted acid like this. Bronsted or protonic acid means it will be donating its proton. So when here the proton, when it is combining with some initiator right here, it will donate its halogen and then it will form something like this R dash C plus and A minus the acid group by CH3. So what happens here is that once this kind of group is formed, the strong protic acids can be used to form the cationic species. And once this cationic species is formed, uh, if the anion of that acid it's very highly nucleophilic, right? It will terminate the protonated olefin by combination. Why? Because this will again combine back here. So because of this, it will get terminated. And because there is a charge and difference, and it will be searching for the other charge, and it will
So it will
terminate.
terminate with the acid itself, with HA
Yeah,
itself.
yeah, and that's why it will terminate the protonated olefin by combination. It will again combine and terminate. That's why. Okay.
Okay, this is true then. Okay,
Yeah.
next please.
Hmm. Then we have for a compound to act as a cationic initiator in ionic polymerization, it should be less nucleophilic. Why? Because in the previous question, we saw that anionic,
Highly nucleophilic means it will terminate,
yeah,
right?
exactly. So that's why it should be less nucleophilic. So from that itself, you can infer this. Okay.
Yeah, clear, clear.
Then for a compound to act as a good cationic polymerization initiator, the following properties are required. Choose the correct options. Electroinitiation is possible where either monomer, solvent, electrolyte, or any other active species can initiate the process via electrolysis.
So this is like all the okay. Electroinitiation is possible. All the three
Hmm.
options.
Yes, yes, exactly.
Okay, initiation via electrolysis process
It
or
is
initiate.
electroinitiation is possible.
Oh, electroinitiation. Okay, that's why
Mhm.
indirectly we calling it as electrolysis.
Yeah, yeah, yeah.
Okay, okay.
Okay.
The amount of
Then this is like a general question where you have to remember the value of
9
how.
electron volt.
Hmm,
The
exactly.
last one.
9 electron volt. Correct. That is the.
Okay.
Then it is about ionophores. Mm,
It is forming with liquids will be condensed. Mobile carrier nanofoods. Okay, it is mobile carrier nanofoods, right?
Hmm. Yes, yes.
Yes. Okay.
Then what are the conditions required for achieving a nanomolecular weight polymer during ion polymerization? Uh,
Narrow molecular weight. So
yeah,
narrow molecular weight. So it should be very narrow. Wide
yeah.
chain transfer rate, low termination rate, low termination. Okay. Then the rate of initiation equal to rate of propagation. Okay. Rate also whatever. Okay. Rate is the same rate if it is propagating. It should be like all the chains should be like similar. Like it should have
Hmm.
similar chain.
Exactly. Yes.
So then option three is
Hmm. Yes, yes. Option three will
correct
be
now.
correct.
Not all of the above. It is only option three. Correct now.
Yeah, yeah. Only option.
Okay.
Then we have which of the following can be used as experimental methods
For
for
determination of
determining the absolute weights.
okay, okay. Um, for determination of short stopping of polymerization, termination of trains. Experimental method means UV visible
Yes.
because other two things is not like otherwise we have to stop the reaction and take it and do it, but that is that will not
Yeah,
change.
one of them is not like the other. That's what it is.
Pardon, yeah, pardon.
One of the methods is not like the other methods. It's like the only way to how you can do it. First of all, UV vis will be very helpful as the polymerization process will keep going and keep increasing the mass of the polymer. The visible spectrum, UV or visible spectrum will be changing based on the rate of the reaction. So UV vis is one of the answers. Okay,
Yeah,
UV vis,
no
yeah.
problem.
Uh,
Okay.
and short stopping of the
Because
polymerizing
that I
system.
have a doubt. In case if you want to find the rates, you can stop
No,
the reaction at some point, take the sample and see how much it has progressed.
yes, yes,
Whether that is also there in that case, or but real time kinetics we can study, but UV visible at different
yeah.
time you take the sample, then
Hmm.
give the UV spectrum, you see how much it is the new molecules formed or new systems are
Correct,
formed.
correct. Okay, so that is the case. So whenever you are defining the polymer weight with respect to the number of units which are present on top of it, right? Uh, uh, that is the molecular weight of a polymer. Now, the distribution in the molecular weight category is number average molecular weight, weight average molecular weight, and viscosity average molecular weight. These three are the basic ones. There are others also, but we will discuss these three first. So, what happens in number average molecular weight is we are defining the polymer's molecular weight with the number of the chain which is present in the highest order. Example, there are 10 chains. Okay, 10 chains in a polymer. Now there are 10 chains present. One of the chains weight is 60, and that 60 number chain is actually repeated at least 6 times in this distribution of 10 chains. So in this distribution of 10 chains, 6 chains have the weight of 60. It means that the chain which is having the number 60 is the most dominating one in this entire distribution of 10 polymers. So the entire weight will be focused on this 6 chains only. So that's why that distribution is called the number average molecule. You are averaging the entire polymer's weight with respect to those 6 chains and then counting the other four rows. That entire average will be shifted towards the higher number of the polymer chain, particular polymer chain. Okay. Next, we come to the weight average molecule. Now, what happens in weight average molecular weight is, let's take the same example. You have 10 chains. Now, as I said, the six chains are having 60 molecular weight, but there are let's say three chains, which are having 100 as the molecular weight, individual molecule, 100. So what happens in this case is the weight of these three. is much higher than these six present right here. Okay, so it's basically they're balancing each other. So you can say that these three are much higher in weight, so the average of the entire polymer chain will be shifted towards these three. And in that case, that is called the weight average molecule. Okay, so that is how you define the weight average molecular weight and the number average molecule. So polydispersity index is defined as the ratio of the weight average molecular weight divided by the number average. It's the ratio between these two. So with this ratio, what we can tell is that what is the dispersity of the chains, the chains and the distribution of the chains present inside the polymer mixture. Because always the weight average molecular weight of a polymer will always be higher than the number average. Why? Because in a polymer mixture, usually short chains are present in a much higher quantity than the longer ones. So what happens there is these short chains will always dominate. But since the weight of the long chains is much higher than these short chains, weight average molecular weight is always higher than the number average. So when you divide the weight average molecular weight divided by the number average molecular weight, so that will give you your polydispersity index. So first statement is correct. Now, whenever this weight average molecular weight and number average molecular weight is same, it means that the polymer is having all chains of uniform length and all of them are considered for the weight. But this is not at all possible for real polymers because that is a ideal situation. We cannot achieve that in any kind of polymerization method. We might try to achieve it, but the closest we can come to it is around 95 to 98%. So that is only so this polydispersity index is one for only the monodispersed polymer. Monodispersed polymer means all polymeric chains are equal in length, and it is always greater than one for actual polymers. So this second statement is also correct because in real polymers, what's going to happen is weight average molecular weight will always be higher than the number average molecular weight. We know that. So in real cases, weight average is always higher than number average, and so the polydispersity index will always be higher than one. So it will be 1 point something, or maybe two or three also includes, like the order of magnitude is higher. It is only is equal to one for the monodispersed species, and that is the ideal case of a polymer. I hope I'm still audible and the
Yes.
presentation
Yeah,
is visible.
clear. You're audible.
Okay. Okay. I'll move on to the next one. Uh, this is a simple one. What
Just
is the
one small clarification.
yeah, yeah,
Sorry to, yeah, this actually just for average molecular weight,
yes,
weight average, number average. Yeah, when we say number average, it is the number of, it depends upon the number of individual molecules like monomers,
yes.
which is getting attached to the polymer. Weight
Uh,
average generally adds to that individual monomer weight into the number of monomers together, like
yeah, yeah,
sigma n
correct, correct.
by sigma ni mi by sigma ni, like that we used to put it that way.
Yeah, yeah, correct.
You have explained certain specific point into that. I am just having some lack of clarity on that weight average part. That alone,
Oh,
can
okay,
you
okay.
please
Yeah, okay. I'll just explain it to you again. Okay. So imagine that again. Let's take the same example for the 10 chains. Okay. So we have to create a distribution for this. Okay. Let's create a distribution for this. In this distribution, this is the let's say the distribution factor or the cumulative frequency, and then here we have uh, the molecular weight. Okay, example we have the molecular weight, and this is the frequency, or you can say the fraction. This is the fraction. Okay, fraction. So the polymer distribution looks something like this. Okay, and on this curve, the number average molecular weight is present somewhere here. So this portion is called NN. Why? Because this is the number average molecule. and weight average molecular weight lies in front of it. So you can clearly see that number average lies before and weight average lies in the front. This is NW. Okay. So how we define the weight average is that weight average molecular weight is defined as the average taken from the point of view of the heaviest chains. Okay. The chains which are the heaviest, when you derive the molecular weight from that point of view, that is your weight average. And number average molecular weight is when you are taking the average from the point of view of the chain which is present in the maximum number in that polymer group. It's like,
Okay.
uh,
So
yeah,
more like if you are having multiple chains, small and big,
yeah,
number average will dominate with a smaller number of chains, multiple, which is more.
yeah, yeah.
Weight average, even if it is a bigger, if it is having higher molecular weight, will consider that for weight average evaluation.
Yes, exactly. So the thing is,
Okay, clear.
yeah, all polymer mixtures will have number average also, weight average also. Okay, so that is one. The
Yeah,
third
yeah.
one, yeah, the third one which I talked about was the viscosity average, and it lies somewhere in the middle of these two. Now, how viscosity average is defined as when every polymer is soluble in some sort of solvent. Okay, so whenever that polymer is added into that solvent, the polymer chains, right, they dissolve and they open, and that will increase the viscosity of that solvent. Now, what you do is you measure the same amount, like you measure the viscosity of the solvent when it is present in its native state without any polymer, and measure it when it is present with the polymer, with the increased viscosity. This difference in viscosity, it will give you a measure of the molecular weight, and that lies in between the Mn and Mw. That is called the Mg, viscosity average molecular. Uh, to determine the molecular weight, usually the one instrument which is used is gel permeation chromatograph. Okay, so this is the process which is used, and in that instrument, what we do is we dissolve the polymer in some solvent and then pass it through a gel column. And in that gel column, the chains which are heavier in weight are retained, and which are lighter. Sorry, the ones which are heavier are passed through first, and which the ones which are lighter get stuck inside the gel pores of the column. And with that, you will get a distribution which will give you the determination of all the molecular. So that was just some extra information. Maybe it won't be that much relevant for you, but that was just some extra information regarding the point. Moving on to the next question.
Yeah, clear.
Yeah. What are the other classifications of suspension polymerization? We have bead polymerization, powder polymerization, and emulsion polymerization. I guess this is a very straightforward question. So suspension polymerization's other classifications are bead and powder polymerization. You might have already, I think, seen in the course itself, and it's present in the course notes also, how the bead polymerization forms. Whenever the monomer polymerizes and the polymer is present as a perfect bead and it separates out as a perfect bead is called the bead polymerization. And in case of powder polymerization, whenever it's not separating as a perfect bead and it is present as small molecules is called the powder polymerization. And they are like just the parts of suspension. So these two are the correct answer for this question. Moving on. The polymer synthesized by suspension polymerization process among the following is polystyrene, styrene butadiene rubber, nitrile rubbers, vinyl acetate, homopolymer, and copolymer. So in this, polystyrene is the one which is prepared by the suspension polymerization. So I have given the reaction for the polystyrene uh, suspension polymerization. Basically, it goes in the initiation, propagation, and termination steps like we discussed in the last class. These kinds of questions are more like, what should I say? You'll have to read about them, and only then you will get to figure it out. There are different kind of questions where somewhere you have to apply the scientific concept, and in some cases you'll have to just maybe remember all these parts. So here you can see that how the styrene molecule is present, and then there is a radical. The radical initiates the makes the initiation step. It attaches, and then we have a free lone pair right here. And then because of the propagation, it attaches to the other molecules, also styrene molecules. And then you have the uh, polymer chain forming. And then the termination occurs when two free pairs come together, and then they terminate the reaction. So the chain is complete. So polystyrene is the one which is produced by the suspension polymerization. Styrene butadiene rubber is produced by emulsion polymerization and solution polymerization. Moving on, which is incorrect for the suspension polymerization process. It is there are four options. It is carried out in continuous stirred batch reactor. Initially, the monomers are dispersed in continuous liquid phase with agitator. The spherical polymer particles formed are in the range of 50 to 500 micrometers. And fourth is the control of the particle size distribution is not an important issue in this process. So for suspension polymerization, definitely the incorrect answer for this, we can clearly see that control of particle size distribution is not an important issue is the answer for this, because definitely the size of the bead or how the polymer molecule is forming is of utmost importance. So again, you can answer these questions quite easily by just reading the process description and what are the parameters involved in the process. So the learning about the process parameters of every polymerization process can suffice to answer such questions. Moving we have which one of the following properties of polymer is desirable during the synthesis of polymer. Now, this is the question where it is important to know the concept of the polymers. So first we have the low molecular. Now, if your polymer is having low molecular weight, definitely it will have lesser viscosity. So it will become much more handleable during the synthesis of any kind of polymer. So that is the correct answer. Next is impurities. If any impurities are present inside the polymer, what would that do? It will basically stop or hinder the synthesis of the polymer. So that is undesirable. Next, we have the low viscosity. Now, low viscosity of a polymer is basically, as I said, the first point and the third point are quite synonymous. So I would say that low viscosity of a polymer is very important because handling of the newly formed polymers is quite a difficult task sometimes. And because of that, also heat fluctuations can occur because as polymers form, polymers are basically thermal insulators. So to control the temperature of the reaction or maybe how the polymerization process is going on, the rate at which the polymerization reaction is occurring is also difficult to control. So that's why low viscosity is quite important, but the molecular weight part might not be correct all the time. Why? Because maybe you want to manufacture a polymer with higher molecular weight, and maybe somehow during the synthesis you would want a low viscosity. But this can be achieved by dissolving the higher molecular weight polymer in some sort of solution. So basically you go for something called solution polymerization in that case. So low viscosity would be the correct answer because impurities is definitely not an answer for desirable desirable parameter for the synthesis of the polymer. And lower molecular weight is quite subjective. It depends on the application for which you are manufacturing the polymer. It might be lower, it might be higher, so it depends on it. But one thing which everybody would want during the synthesis would be the low viscosity. So low viscosity is the correct answer. Now we have the completely amorphous polymers show only the glass transition temperature. Next, crystalline polymer show T melting temperature and semi-crystalline polymer exhibits both temperature. So it is asking us what is true and what is false. So So we have two graphs here. I've given you there are two graphs I put here. First graph is actually showing the relation of temperature with the stiffness or the modulus of the polymer. In next graph we have the temperature and the heat flow. So the second graph is actually scanned from a machine called or the process called differential scanning calorimetry. So what happens in differential scanning calorimetry is that you're able to identify the phases through which a polymer or a material goes before deform. I will explain the second graph later. I'll explain the first graph first. So we have completely amorphous polymers show only the PG, glass transition temperature. Now, here we are encountering a term called glass transition temperature. Now, what is glass transition temperature? The name itself suggests that glass transition temperature. So, what is glass? We have the silica. Silica, when it is heated up, it forms glass. All the sand and glass. So, glass is first of all extremely brittle. So that is called the glass one. It's example like it's extremely brittle. So the brittleness of a material is shown by its glass transition temperature. If a material's glass transition temperature is very low, uh, if the glass transition temperature of a material is quite high, it is not going to transition from its glassy state to the rubbery state with the increase of temperature easily. It means that the material will stay brittle. So, for example, glass itself doesn't melt quickly with temperature, and it stays glassy. Glassy in the sense like it's brittle, and it is not able to. It's not that flexible. When you heat polymers, they become flexible, and they start to flow also. So that's why the modulus or the stiffness decreases as the temperature increases. And the first transition which occurs is called the glass transition. It leaves its glassy or the brittle state and goes to the rubbery state. This temperature is called Tg. Means it? That is called the glass temperature. So completely amorphous polymers only show glass transition temperature. Now, what is the meaning of amorphous polymers? That amorphous polymers are the polymers which are not ordered correctly. Ordered correctly in the sense like polymers, whenever they are synthesized, they attain a certain arrangement, and that kind of arrangement decides what are its properties. Will it be more crystalline in nature or amorphous in nature? Now, amorphous in nature means that the polymer chains are not ordered in any particular order. And because of this disorder, what is going to happen is the polymer chains might not have the high mechanical strength. Only crystalline materials will have high mechanical strength in them because the polymer chains are correctly ordered. This ordering allows the polymer chains to pack with each other more densely. So you can clearly tell from the name density itself that you can correlate it with the LDPE and HDPE example. So LDPE chains have slight branching in it. And because of that branching, the close packing is not possible. And because of that, it's not as dense. It will have more amorphous regions in it. Whereas high density polymers have less branching. Because of that, there is something called close packing. And because of that, the crystallinity measure of that polymer, HDPE, will be much higher than the LDPE. So in that case, it will the amorphous polymers will show TG and crystalline polymers will show melting temperature. Why they will show? Now we come to crystalline polymers. Now why crystalline polymers show melting temperature is that when crystalline polymers are heated, because of the close packing, they are able to actually resist the temperature changes quite easily. And they don't flow very quickly because since they are closely packed, the interactions between each polymer chain are quite prominent. Whereas, like compared to the case of amorphous polymers, in amorphous polymers, since there is no close packing, the chains are quite far apart and they are arranged in haphazard. And because of that, the amorphous polymers are not closely packed. In crystalline polymer, since they are closely packed, the secondary forces, for example, hydrogen bonding or any other force, is acting much more efficiently, and because of that, it is able to resist the temperature change much more efficiently. And as the temperature increases further, only melting occurs. Why melting occurs is that the temperature itself overcomes the secondary forces and the chains will start slipping past each other. And when that happens, the polymer starts flowing, and that brings us to the rubbery flow or the rubbery state. So crystalline polymers will straight away go to the rubbery flow or rubbery state. if and only if it's a thermoplastic polymer. Again, going back to the first class, as I explained that thermoplastics and thermosettings, how they are differentiated is that thermosettings are basically interlocked or interconnected through crosslink. And since cross-linking is another backbone bonding, that is much more stronger than any kind of secondary interactions. So that makes them even more harder to deform under high temperature. And the third part of the statement is semi-crystalline polymer exhibits both temperatures. Now the word here is semi-crystalline. The one statement I will tell you now is that all polymers are semi-crystalline. Semi-crystalline means having both uh, parts of amorphous and crystalline. And polymers can have either crystalline structure in a much greater range and amorphous and smaller, or amorphous in much greater range and crystalline as well. But no polymer can be 100% crystalline. If it was 100% crystalline, it definitely wouldn't be a polymer. Because the thing which separates polymer from other materials is that it is moldable and it can be molded and deformed with use of temperature easily. So that differentiates polymer from other materials. That's the exact reason. And that is why polymers don't exhibit 100% crystallinity. They exhibit semi-crystalline. Means some portions will be amorphous, maybe a major chunk will be crystalline. So semi-crystalline polymers exhibits both temperature. So that's why all polymers will show a TG and they will show a melting point. But crystalline polymers, that is, maybe a material is almost 70 to 80% crystalline, its melting temperature will be much more prominent than its glass transition temperature. But always remember this that almost all polymers are semi-crystalline. So now I will explain you what is the second type. Now the technique which has been used here is called the differential scattering calorimetry. Now what is the meaning calorimetry tell you is that whenever you burn something, you are burning it with respect to the calories which it has. Similarly, when heat or temperature is passed through something, how much heat is flowing through that body will give you the calorific value of that material. Okay. So in differential scanning calorimetry, what you do is one, you always compare the unknown material, which is your polymer, or any other material, with a known material. Now, the known material is maybe a metal, which we exactly know how the heat flows through it and what is the amount of heat flow through. So you can see here there is on the x-axis temperature and on the y-axis we have heat flow. That is milliwatt. Okay. So what is happening here is that as the temperature increases, heat starts flowing inside the material. Now, the moment the glass transition is encountered, you can see that the drop is there. And again, here we have a drop. So when the polymer deforms, it is basically uh, what what should I say? It is basically undergoing change because of the heat which is being applied. And since it is undergoing change, heat is flowing through. And since the heat is flowing through it, it is absorbing that heat. And that is the exact reason why the temperature goes down. It goes in a negative point because it is absorbing that heat. So it becomes endothermic in that case. Okay. It is absorbing that heat and then it flows. Starts flowing. Slightly it will flow. And then as it goes inside, you can see that the entire polymer will then melt away and then start flowing. Once it starts flowing, convection can occur. Clearly, convection can occur, and then it will release that heat. It will totally release that heat. Glass transition, you can see that as the temperature goes to glass transition, next we have the rubbery flow. And that rubbery flow comes in during uh, when it goes under any kind of melting or any different like any kind of other phase change. Here also, when the peak comes in, crystallization occurs. Crystallization temperature is the temperature where the ordered crystalline structure of the polymer is disturbed. Entirely it gets disturbed. So you can see that In the glass transition temperature, here the decline shows a transition from the glassy state to slight movement. The polymer might become soft and it's becoming weaker. And as further it goes, we encounter crystallization. And the moment the crystallization occurs, all the crystalline portion of the polymer starts subsiding and all the polymer starts flowing. And then all the energy is given to melt. The entire polymer starts flowing. So this statement that is completely amorphous polymer shows only glass transition temperature, crystalline shows melting point, and semi-crystalline exhibit both is true. So the answer for this question is true. Sorry I took so much time on this question because it was very important for me to make you understand how these three regions work and how these things happen. I guess you
Yeah,
might have some doubt.
I have some small clarification.
Yeah.
This TG and melting
Hmm.
both requires a heat. Probably TG will not induce any phase change, but
Yeah.
melting may
Yes,
induce
yes, yes.
phase change. So
Yeah.
both will absorb the heat, so heat can go negative. And in case of crystallization,
Hmm.
we are seeing in the positive side because
Yeah.
there the crystal start forming and growing, but that is directly relevant. Okay, polymer side, if you are seeing the alignment of the chains,
Hmm.
uh,
Yes. Uh,
that is
yeah, yeah. Actually, I would like to add one thing. Crystallization temperature is never correctly shown in the starting scan of a material. This is actually the starting scan of a material. There is another scan which occurs when you're cooling the material. When you cool the material, at that point again you see a crystallization temperature. And that temperature is the real crystallization. Why? Crystallization process occurs when you cool down a polymer. So when you're cooling down the polymer chains have time to come back together. And once they come back together, they arrange themselves and pack themselves into a crystalline fashion. That is what is called the crystallization process.
okay. My
Yeah.
question is whether it should be the crystallization. Why it is showing positive, like heat flow is on the positive side.
Okay. Another thing I'll add to this thing is that heat flow shown in a differential scanning calorimetry can either be shown by exothermic heat or endothermic. So this scan I would say is present in endothermic heat scan. If it was an exothermic heat scan, you will see that the glass transition will be rising up, crystallization will be going down, and melting will be up. So it depends. What is your scanning mode? Okay. So in that kind of
So
scanning mode,
okay,
you will see that the the graph will be basically inverted. Okay. So don't
okay, fine,
confuse with that.
fine.
Okay. So don't get confused with that because if I showed you the other side of that graph, that is the exothermic or endothermic, the same graph will be inverted. These points will remain the same. It's just that they will be inverted. Melting will be on top, crystallization will be down, glass transition will be top, something like that. Okay. So it
Okay, clear,
depends. It depends on what kind of heat your machine is trying to measure. Fine.
clear, clear. Yeah.
Yeah. So have you gone through the second assignment or the third assignment yet? Have you seen the questions?
Second is submitted. Third, I am yet to start because actually one more course also parallelly going in. Total four courses I am attending this
Oh,
time.
okay. 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 So
So
you're
probably
attending
third
four
assignment
courses.
I am yet to start.
Oh, okay. Okay. Okay.
That
Okay.
is, I
So
think, loaded yesterday only. Uh,
yes, yes.